All right, welcome back, everyone. With maybe one more energy burst, we can get through this last session. So we'll have the final presentations and then a little presentation on the next IBIC and then the closeout. So the first presentation is by Alexander Romanov. He got his PhD in 2011 at the Budker Institute of Nuclear Physics in Novosibirsk, Russia, working at the VEPP 2000 electron-positron collider. He joined the IOTA team at Fermilab in 2014 and worked on the ring design and commissioning for the ongoing and future experiments. As one of the key members of the IOTA team, he participated in many IOTA experiments and is the PI for the series of single electron studies. Unfortunately, he couldn't be here, so he will have a pre-recorded presentation, but then he's available for questions and answers. So let's welcome Alexander.
Hello. First of all, I would like to thank organizers of the IBIC 2022 conference for the invitation to make this exciting presentation on the subject of experimental single electron six-dimensional tracking in IOTA. I'm doing this talk on behalf of a dedicated team of researchers from FAST and IOTA facilities at Fermilab. Unfortunately, due to supply chain disruptions, we were not able to receive all the necessary equipment in time to make experiments before IBIC conference, and therefore the topic of the presentation that I'm making today is better described by proof of principle experiments that demonstrate feasibility of the experimental single electron tracking in IOTA. So, why we are so much interested in a single particle tracking? In my opinion, observation of a truly point-like object, which a single electron is, in a storage ring would allow us much deeper understanding of a single particle dynamics, and that is a mandatory basis for successful implementation of advanced beam control concepts. For example, it would allow us to more efficiently control halo and suppress losses. It would allow us to suppress instabilities in the rings, and eventually will allow us to reach higher beam powers. It's also an extremely valuable machine diagnostics tool. For example, it allows to study betatron and synchrotron dynamics, for example, betatron tunes, damping times, coupling terms. It also allows to directly measure nonlinear dynamics, for example, tune dependence on amplitudes, tracking of invariance of motions, etc. And also it is quite sensitive to residual gas properties. And last but not least, tracking truly point-like object is a direct way to validation of simulation tools. So what is the state of the art with a single electron tracking to this moment? Most of the previous studies were focused on longitudinal dynamics, which is done by detecting time of arrivals of individual photons and basically reconstructing synchrotron oscillations over the time. In previous experiments at IOTA, we used digital cameras to track all three mode amplitudes, two betatron amplitudes and one synchrotron amplitude, as well as we used photomultiplier tubes and single photon avalanche diodes to track synchrotron oscillations in a similar fashion to that done before. So, capability to track only two remaining dynamic variables, namely betatron phases, was necessary to demonstrate full six-dimensional tracking. And therefore, we decided to demonstrate that it is feasible by doing betatron oscillation tracking of just a single electron, or Bob's experiment. On this slide, you can see an image of the IOTA ring. It is a small machine with only 40 meters circumference, and its geometry is shaped by 8 main dipoles, and each of the main dipoles is equipped with optical diagnostic stage. Here on the bottom left image, you can see a complete optical diagnostics stage. Synchrotron radiation from an arc in the main dipole exits vacuum chamber through a window and through a periscope enters dark box with optical diagnostics. In the vertical section of the periscope, we install focusing lens, iris, and filters if necessary. Typical diagnostic setup consists of a single digital camera, but more instruments can be installed if necessary. And soon after we started beam operations, we found out that our digital cameras are sensitive enough and have low enough noise to be able to detect images of just a single electron if exposures are long enough. And by long enough, I mean exposures above about 0.2 seconds. But we were using about 0.5 seconds and 1 second exposures. Of course, such a long exposure times averages out information about phases of the betatron and synchrotron oscillations, but it is still possible to extract information about amplitudes of all three mode oscillations. This slide shows how one can extract all three mode amplitudes from even a single image. For that, we analyze projections on a vertical and horizontal axis. Vertical projection contains information about one mode oscillations, namely vertical betatron oscillations, and projection has very characteristic peaks at the stopping point of the oscillations. And in reality, of course, we measure somewhat smoothed out curve, which is a convolution of this ideal projection and the resolution function of the optical system. In horizontal plane, if the dispersion is non-zero in the observation point, we measure a convolution of two modes, betatron mode and synchrotron mode. It again has two sharp peaks that tells information about bigger amplitude mode, and the smaller amplitude mode is responsible for the width of this shoulder. And it is a big advantage when you compare to multi-particle beams, because typically multi-particle beams of electrons in storage rings form Gaussian distribution, and the convolution of two Gaussian distribution doesn't have any characteristic features that gives you information about smaller amplitude. And moreover, the overall size of the Gaussian bimode distribution has only root mean square contribution from the smaller mode, which is very hard to detect. In practice, we didn't use images from just a single camera. We used synchronized sets of images from all the available cameras, and here you can see such a set from 7 cameras with corresponding projections. IOTA lattice parameters were precisely characterized using local algorithm, and that gave us accurate information about camera tilts, calibration coefficients, beta functions, dispersions, and many other important parameters of the lattice. And therefore, only a handful of parameters remain to be found, most importantly, amplitudes of the modes. On the bottom right, you can see a single electron evolution in the IOTA ring captured by one of the cameras. You can see that it is nothing like a stationary Gaussian distribution. There are stopping points that randomly change in time due to random kickbacks from synchrotron photons and interaction with residual gas atoms. Most notably, residual gas interactions manifest themselves in vertical plane, which you can see sometimes. This slide shows evolution of mode amplitudes over about 500 seconds. Dynamics of amplitude for betatron horizontal oscillations mostly defined by random kickbacks from synchrotron photons, although there is some small effects from interactions with residual gas atoms. There are also two big events that you can see in all three planes that are created probably either by high amplitude scattering on residual gas or glitch in the power supply system. Longitudinal damping time was comparable to the exposure time, and therefore what you can see here is somewhat average dynamics of the synchrotron mode amplitude. In the vertical plane, amplitude dynamics was defined by random scatterings on the residual gas atom. You can see abrupt changes in the mode amplitudes with the following exponential decay. Statistical analysis of this data yields mode emittances, damping times, some properties of the residual gas atoms, and from damping times we also can deduce beam energy. So, digital cameras allow us to track three mode amplitudes. PMT in addition allows us to track phase of the synchrotron oscillations and their amplitude with much higher precision when compared to digital cameras actually. What's left are two phases of betatron oscillations. And because Betatron oscillations are much quicker when compared to synchrotron oscillations, electron typically does about 5 oscillations per one period in iota. It was an open question whether we can track it or not with such a sparse data as detection of photons, because we only detect about 1 photon for every 2,000 revolutions. To check if it is possible, we made a slight modification to the PMT setup. So in this box we had a camera on a translation stage that allowed to move it in and out and to position exactly in the focal plane of the optical system. So the straight edge was positioned exactly in the same plane as the image to make sure it is in the image plane, and we could insert it to block exactly half of the beam image. That allowed us to let only photons from one half of the phase space to reach PMT, converting it to a very crude position-sensitive single photon detector. To see what to expect from such a crude detector, I made a very simple simulation, assuming purely harmonic oscillations with statistical properties of the radiation that we see in iota, which is 3,700 counts per second, or about 1 photon every 2,000 turns. I simulated 50 microseconds or 400,000 turns with about 180 photons detected. Here you can see a contour plot of the likelihood function that written here. It's basically a count of the occurrences of the electron at the photon emission turn in the right half of the phase space. It depends on the Betatron phase and on the Betatron tune. And here you can see a clear peak in the data. So 180 photons over 400,000 turns allows us to have about 2% precision of the phase reconstruction and a very fine measurement of the Betatron tune, because the extent of the Betatron oscillations over which we feed data is quite large. To assist this experiment, we designed and commissioned special lattice with several favorable parameters, such as big horizontal size in the observation point, low dispersion to reduce coupling with synchrotron oscillations, and long damping times. Let me temporarily jump to the main result of the BOPSI experiment, which is shown on this plot. Here you can see a clear peak that corresponds to the proper Betatron tune of a single electron that for the first time was measured using just a single electron in a storage ring. And that is the last obstacle on the way towards the full 6-dimensional tracking, because it proves that it is in principle possible to detect phases of Betatron oscillations in the storage ring. There are many complications in the analysis of data from such a crude detector as shaded PMT. For a purely harmonic oscillations of an electron, there are 2 parameters that we need to search through, and there are only brute force approach to this search. Any deviation from harmonic oscillations would add extra dimensions into that search space, and even searching in a 2-dimensional space is quite a hard process. So what are those complications that deviates oscillations of a single electron in real machines from purely harmonic ones? First of all, Betatron tune depends on the mode amplitudes of an electron. There are chromatic effects, and therefore synchrotron oscillations where energy and momentum of electron on every turn changes a little bit from its equilibrium value affect what the Betatron tune is through the chromaticity, and also changes a little bit position if the dispersion is not 0 at the observation point. Luckily, this we do not need to search, because we measure exact parameters of the synchrotron oscillations, we know chromaticity of the Betatron oscillations, and we can account for this effect. There are also tune dependence on Betatron oscillations, and in principle we can use digital cameras to measure and track Betatron amplitudes. Unfortunately, we didn't measure very well synchronized data set, and analysis of images is still, and alignment with the actual data is still in process. There are also other nonlinear dynamics effects, such as fringe fields of the quadrupoles, some nonlinearities, imperfections in the magnets, and so on. And they are very hard to account for because there are way too many variables to be able to fit using this coarse data from shaded PMT. And lastly, but not probably least, if there are power supply ripples, for example, quadrupole changes current a little bit, that also would change Betatron tunes and would affect extent of the possible reconstruction of coherent oscillations in Betatron plane. To account for synchrotron oscillations, we reconstructed their parameters over the entire dataset. The top plot shows you relative time of arrival of photons as detected by PMT, which has about 1 nanosecond precision, from turn number on which it was detected. You can see that they cluster around average beam arrival time, but the spread changes in time, which is a signature of changing synchrotron amplitude. Every synchrotron period takes about 14,000 turns, and with on average 1 photon detected every 2,000 turns, we should expect about 7 photons for every synchrotron period, which is well enough to fit a nice sine curve to the oscillations. We split this raw data into sections of 400,000 turns, and each section was fit with a sine wave with phase, amplitude, and tune as the free parameters. And here you can see a zoom in into one of such sections. The middle plot shows evolution of the amplitude in time, and you can see that the chosen window is adequate because window-to-window variation in amplitude is not that big, and it is quite smooth actually. As a byproduct of this analysis, we, for example, can look at the dependence of synchrotron tune on synchrotron amplitude, which is not a straight line, as you may expect, but has a slight dip for the higher amplitudes. And if you do accurate simulations, it is what you actually expect from this plot. Apart from accounting for synchrotron oscillations, there is another trick that we can do to make it a little bit easier for the initial search of the parameter space. And we can use to our advantage that the photon radiation process is a random process with exponential statistics. Here on the left plot, you can see actual experimentally measured detection intervals between each photon, and it nicely follows exponential law. But this fact allows us to handpick periods of times when photons arrive more frequently to the PMT, and therefore form a more dense data subsamples. For example, here you can see statistics for intervals that it takes to detect 20 photons. And although the peak is close to 40,000 turns, which you would expect, but there is a tail with much more frequent detection rates. And if you go even lower in number of photons, for example, 4 photon detection intervals, and zoom in into most frequent events, you can see that there are about 300 events when it took less than 300 turns to detect 4 photons. And remember this, I will present some data for this kind of data streaks. Now let's step back a little bit and see how to account for synchrotron oscillations. To the first order, Betatron tune dependence on momentum can be written as this. And here you have chromaticity, momentum oscillations amplitude, and synchrotron oscillations with their tune and phase. If you integrate it, you can arrive to Betatron phase for the given number, and again you can use likelihood function, which is just a number of photons that occurred on the right half of the phase space at the given turn. So let's see what accounting for synchrotron oscillations does to the likelihood function plot. I mentioned that we can use hand-picked data regions from the whole data set. And here is averaged likelihood function, or better say, summed likelihood function for these most frequent detections of 4 photons, so 299 samples. And even assuming just purely harmonic oscillator, we can see a nice, actually quite nice peak around Betatron tune. If you account for synchrotron oscillations, the peak gets much sharper. And then if you go to streaks of 20 photons, and we take the most frequent of them, that, for example, take just under 20,000 turns, then it's more than one synchrotron period, and therefore, if you don't account for chromatic effects, they smear out signal completely. But accounting for synchrotron oscillations yields a nice narrow peak, and you can see that the range in the Betatron tune gets much narrower compared to data streaks that span 300 turns. Now, there are still quite strong unknown effects. If I compare my likelihood function plots to those that I expect realistically from the system, say, for example, if my image is not focused properly, if I don't position my straight edge right at the 50% mark, right at the middle of the image, I still should expect quite sharper peak compared to what I have if I do my best. So here you can see the corresponding plots. So how precise is the chromaticity reconstruction method if you use the single electron data? I would say it's not so bad, because you can see that if I change chromaticity by plus minus 10%, the likelihood functions start to deviate and yield lower peak already. So I would say that's about 10% accuracy, which is quite good for our purposes. We also measured Betatron tunes using conventional methods where you inject macroscopic beam and use electrostatic pickups to measure turn-by-turn coordinates of the kicked beam. I measured it for several kicks amplitudes, and here you can see in the blue dot Betatron tune measured by conventional method. And here you can see data point from single electron measurement. And I would say that corresponds to much lower amplitudes of the oscillations in Betatron plane, and I trust this value more than obtained from high amplitude kicks, which is also a very nice feature if you want accurate measurements of Betatron tunes. But why at IOTA we are so much into single electron tracking? The answer is quite simple. We are not fully satisfied with pencil beam approach that we initially relied on. In that approach, we inject macroscopic bunch into IOTA ring, let it damp to natural emittance and momentum spread, and use it as a macro particle to map nonlinear lattices by kicking to various amplitudes and recording turn-by-turn coordinates. Unfortunately, in strongly nonlinear systems, even beam with quite small size and momentum spread decoheres rapidly. So here you can see sample data from one of the strongest nonlinear lattices, where after only 30 turns, dipole signal vanishes pretty much completely. And that doesn't allow us to track conservation of invariance of motion. On the other hand, single electron is a truly point-like object, and therefore it would decohere only after about damping time, which is millions of turns. On the downside, we have to work with very sparse data. After successful proof of principle studies of single electron tracking at IOTA, we received funding that leveled up our capabilities. For the first stage experiments on truly 6-dimensional tracking, we purchased two 16-channel PMTs. that initially supposed to be used during this summer, but unfortunately experiments were postponed to the late fall. These compact PMTs has very good time resolution, and most importantly would allow us to use just PMTs for measurement of coordinates in X and Y planes, and therefore we would be using just PMTs for the reconstruction of all three mode amplitudes as well as three phases of the mode oscillations. For the second stage studies, we would rely on MCP-based detectors that offer exceptional spatial resolution and very good temporal resolution. Together with truly two-dimensional measurements of the photon and therefore electron coordinates, we would be able to study coupling effects and truly nonlinear dynamics of the electron in IOTA ring. In summary, I would like to say that IOTA is ready for the first experiments on six-dimensional tracking with single electron. Even readily available instruments with small additions allow precision measurements of many important parameters, such as equilibrium impedances, momentum spreads, damping times, beam energy, true Betatron tunes, and chromaticities. Position-sensitive photon detectors will enable an even deeper analysis and understanding of storage rings, which is crucial for successful design, commissioning, and operations of future accelerators. Thank you for your attention, and I'm ready to answer your questions.
Right. So that was a very unique experiment and a great presentation. Any questions? Okay, over there. Patrick.
Thank you for the nice talk. Can you hear us okay?
Yes, I can hear it.
Good. I was wondering, you were talking about the comparison in Betatron tunes, what you call the natural tune versus when you give it a horizontal kick. My question was, can you give it a large amplitude kick in order to probe some dynamic aperture issues in a storage ring?
Yes, we actually did this kind of data acquisitions. It's just a little bit hard because we were in a time crunch at the very end of the run, and the synchronization was not the best. So it's a little bit harder to tag those time intervals when we kicked beam. But in principle, yes, we, especially with 16-channel PMTs, we plan to do amplitude scans and not only rely on random processes to excite amplitudes, but also do it in a controlled manner by just kicking a single electron with the same kicker as we use for injection and for pencil beam approach.
Thank you.
Any other questions? If not, let me ask one. So this is a pretty unique measurement that you had to do. And from your presentation, it looks very well thought out. But were there any new directions you had to take during the experiment? So was it, were there any anxious moments? It's quite unique measurement.
Oh yeah, so it took a couple months to actually extract data, and that's why I was even recording that presentation, remembering that moment when I first saw signal was very exciting, because you can imagine after many weeks of trying to find some useful signal in the random data, it was not easy, and probably the most useful thing was to handpick the most frequent photon arrival events. Because of exponential law, it tends to vary significantly the frequency, especially if you consider short tracks. So yeah, I think there are much more surprises to ahead of us when we will get much more precise data. But there are quite a few moments where we either didn't get what we thought we should get from the very beginning, or when it took much longer time to get to the actual answer.
Yeah, thank you. One more question.
Here it is. Sorry, behind you.
Thank you for the talk. How long did it take for you to get to 1 electron? And how?
Oh, that's thank you. Yeah, that's a very well established process. So we can achieve single electron quite in two various ways. First, we can just reduce bunch current from the injector by using dark current and then inserting some OTR foils, and it nicely puts on statistics with about 30% chance to inject single electron. On the other hand, if we inject more than 1 electron, we can reduce RF voltage, which in a controllable way reduces lifetime. And again, it's a statistical process, so you can lose all electrons, but if lifetime is a few tenths of a second, you have a very good chance to catch condition when you just have 1 electron and recover the ref parameters that gives about 10 to 30 minutes of lifetime, which is natural lifetime for iota.
So okay, that was my other question. How long? What was the lifetime of 1 electron?
It depends on the residual gas and the lattice parameters, but typically it's between 5 and 30 minutes.
Thank you.
Okay, thank you. If no more questions, let's thank the speaker again.
Thank you.
Thank you, Alexander. And our next speaker will be Joanne Wonzink. Hope I say that right. Graduated in applied physics in Krakow, and since 2020 she has been working on the luminosity measurement as part of the CMS beam radiation instrumentation and luminosity project. Her PhD project is a collaboration between CERN and EPFL, focusing on the luminosity measurement with fast beam condition monitor and beam systematic effects on luminosity, supported by charts. And she will be presenting on this. Right.
Yes. Thank you very much for the introduction, and thank you for giving me the opportunity to present here today. I'll be talking about the upgraded CMS fast beam condition monitor, shortly BCM1F, for the LHC Run3 online luminosity and beam-induced background measurements. So BCM1F is a part, as already mentioned, part of the beam radiation instrumentation and luminosity project at CMS, which is one of the main LHC experiments. And it is a dedicated standalone luminometer, as of course the luminosity is the key parameter. And it is independent from all central CMS services. It is a very fast detector with sub-bunch crossing precision, which enables the measurement of the beam-induced background. It was already working throughout the previous LHC runs, and it shown a very good and robust performance. At the time, it used mixed sensors, so there are the various types of sensors, the single and polycrystalline diamonds, as well as the silicon. However, at the end, the signal-to-noise separation and as well as the response linearity proved to be much better for the silicon sensors. Hence, during the long shutdown 2, the BCM1F was upgraded with new silicon diodes, and it's presented with the current version here at the bottom. So the quadrant of the BCM1F, which is called also C-shaped. The whole detector assembly was the process in the time of 2020 and 2021. each of the detector, so detector was qualified basically by the quadrant, and you can see, so this is basically the pictures for the overview of that process. So you can see one of the quadrant being assembled here. So it's one of the C-shape, and if you take the two of the C-shapes, they form a ring around the beam pipe at approximately 7 centimeters. The whole system has 48 channels. And yes, and then the BCM1F is integrated into the common structure. In the middle, there is this quadrant of a full detector, together with the pixel luminosity telescope, which is in front of the BCM1F, as well as the beam condition monitor for losses, which are the small cages here, including the diamonds at the back of the BCM1F. And so as soon as the carriage was, all the carriages were qualified and ready, they were moved into the CMS volume and then installed inside the CMS volume at 1.9 meters from the interaction points, so that to minimize the material that can be activated in front of it, so there is just a pixel barrel in front of the BCM1F. So the first checkout of the detector was done already in at the end of 2021, when there was the pilot beam test at the LHC at 400 GeV. So here's the overview, or the diagram of the full BCM1F system, and I will firstly focus on the left-hand side, of that diagram, which is the front-end part. And so, as I already mentioned, now we use the silicon double diodes, which were initially designed for the phase 2, so for the high luminosity LHC. And any signal induced by the ionizing particles crossing the active material are then shaped and amplified at the dedicated asynchronous and very fast and radiation hard ASIC. And then we have the optoelectronic transmission. So it's actually installed a little bit further from the IP to protect, to decrease slightly the radiation level that it's exposed to. And there the current is converted into the infrared light and propagated into the backend systems and at the CMS service cavern. So on the, actually at the signal, this optical signal is duplicated and then at the back end and propagated into the two parallel systems, the VME and micro-TCA based systems. So I will firstly mention the VME system, which is the baseline used already at the run 2, and it uses the leading edge discriminator with a fixed threshold, and then the signal is signal is processed at the real-time histogramming unit, where the orbit occupancy histogram is created with granularity of 4 beans per bunch crossing. And at the same time, we also have the micro-TCA system, more modern system, mentioned as the improvement, which is the FMC-based digitizer with a sampling frequency of 1.2 gigahertz. And there the signal is digitized and processed at the separate FPGA. So it has basically sampling precision without any latency. And then the orbit occupancy histogram has a slightly improved timing with 6 beans per bunch crossings. And there is also another advantage that I will talk about more in the moment, that we can apply a dedicated algorithm for the peak finding. These two systems are connected to the dedicated Brill DAC software, which is also independent of the CMS central services. So there the data is processed and stored. So I mentioned that we have the new micro-TCA based system, and the advantages is that we can apply the more sophisticated algorithm for the peak detection, and for BCM1F we implemented the derivative-based threshold peak finding. And it basically, it's meant to maintain the efficiency even at high pileup, meaning the high number of proton-proton interactions in the single bunch crossings, which is important also for the future high-Lumi LHC. And so the raw samples are the process at the PGA where the derivative is calculated as a smooth noise robust differentiator, and then the peak detection is happens when this derivative crosses a threshold or the zero crossing, depending on the setup. And so this algorithm was implemented, it was designed so that there is the noise suppression at the high frequencies, so it's a perfect differentiator at low frequencies, but and acts as a low-pass filter. So, and then if we take this derivative and integrate again the samples, we obtain the amplitude spectra that you can see at the bottom with a very nice minimum ionizing particle peak and its separation from the baseline the noise, which is here cut out basically for the online setup. And then this new system had to be fully commissioned at the beginning of run 3. So as I mentioned already, we had in 2021 we had the first checkout. So the last thing to do was to optimize the per channel timing of the detector. And then you can see an example of the LHC measured orbit in this plot. And there we can differentiate low occupancy signal coming from the circulating beams, which is followed by the set of trains inside, which is happens during the nominal operation, and then there are some individual peaks here. Somewhere here. I cannot point exactly. So there are also some individual peaks which correspond to individual colliding bunches. There is also one interesting characteristic of this plot, which is the long afterglow tails after each set of bunch trains, and this is caused by the signal, by additional hits which are due to the activated detector material. So this contamination can be corrected for, and is actually corrected for already with the online measurement, and it is done by applying an afterglow correction for each colliding bunch. So each of the bunch signal here would be corrected for afterwards, so that we can include all of the bunches in the total instantaneous luminosity measurement. And this factor, the correction factor, is obtained from special special runs when we have two well-separated. For this case, we had two well-separated single colliding bunches, and so that we can observe how the following bunch crossings, the signal tail in the following bunch crossing looks like after the colliding bunch. So basically, from that field, the data was aggregated over a long time, and then we feed an exponential factor to extract the correction applied. And then you can also maybe notice that this is the logarithmic scale, so actually this correction factor is very small. But is of course very important for the precision luminosity measurement. So one of the main functionalities of the BCM1F is the beam-induced background measurement. And what background is for CMS is mainly the contribution from the beam interacting with the beam gas, as well as the contribution coming from the aperture limits. And you can see an overview of that measurement in the plot on the left along the LHC life cycle. So you can observe how it increases along with the LHC energy, and then there is a step change as soon as the luminosity appears, so when the collision actually happen. In the bottom plot, there is also for reference, the measurement of the vacuum pressure around the BCM1F location show, and you can see how the vacuum levels deteriorate at the moment of the beginning of the collisions. So this measurement is very important for CMS, as it guarantees the safe operation for other CMS subsystems. So there are basically some interlocks allowing or not allowing other subsystems to turn on. But it is also used by the LHC as a real-time feedback about the conditions at the CMS. And how this background is actually measured. So the BCM1F channels, the different BCM1F channels are used for the two beams. So you can maybe see in the scheme on the left that the channels on one side of the IP are used to measure the incoming beam 1 background, whereas on the channels on the other side, they see firstly the beam 2, so the incoming part of that background is measured with this channel. So what it means is that the beam direction is resolved by depending on the time of arrival. But the most crucial for CMS is of course the luminosity. And for the BCM1F is measuring the luminosity based on the zero counting algorithm that I show here. And so it assumes the Poisson distribution of the probability of the hits inside the detector and calculates the mean value based on the probability of no hits. And so this gives us only the mean value, and to actually obtain the absolute luminosity measurement, the detector has to be calibrated, and this is done during the Van der Meer scan, which are like symbolically shown in the figure on the right. So during this program, we have multiple various scan setups, but the main idea is to move the beams in the two transverse directions separately and observe how the rate inside the detector changes. So if as soon from that we can extract the constant, which is called the visible cross section. And after we have a full detailed analysis on that, we are able to extract the luminosity directly from the measured rate. And however, this Van der Meer program is only planned for the end of this year. So currently, we can only use the emittance scans, which are similar but much shorter and much narrower scans to obtain a preliminary detector calibration. However, these emittance scans they were already introduced in Run 2 as a part of the nominal operation of the LHC, and this means that we can make that measurement repetitively. And this is shown on the figure here. This is more or less a month period of the early Run 3 operation. And you can see that the repeated measurement of that constant is very stable. So we achieved the 1.4% on the RMS of the stability of the sigma visible. And this is also shown here for the quite wide range or single bunch instantaneous luminosity. So this is the average sigma visible, but of course then we can study how it looks per channel, because it's intrinsic to each luminometer, and then we can treat each channel as a separate luminometer. And then we also check that we have a very good agreement for all of the channels with 50% spread from the average. So we can use the same separation scans not only for the luminosity, but we can also observe how the beam overlap changes, or to study the bunch profile. In the nominal conditions, it's a little bit more complicated, since we have the geometric factor coming from the crossing angle. But still, I would like to show here the example of that measurement during the LHC nominal operation with the beta star luminosity leveling, beta star meaning the beta function at the interaction point. And you can see with squeezing the beta star from 60 centimeters to the smaller values, the overlap is also decreasing. This is a single bunch, so it's basically the full field with the squeezing steps. And then we can go a little bit further to estimate the convoluted width of the bunches. that are colliding and try to estimate the emittance. And I showed the example of a specific LHC field when the machine was filled with a very wide range of the bunches of various emittances. And we obtained the measurement using the BCM1F. And this is still the work which needs to be compared with other systems. So what else we can actually observe with during the separation steps? Then from fitting that Gaussian-like function, we can also take the peak value, which indicates the orbit displacement for that bunch. And so you can see the example. Sorry. You can see the example of such measurement in the plot on the right. And of course, these displacements are dependent on the number of parasitic collisions and so on the filling patterns. But we can clearly see the train structures in both of the planes, which are shown here. And you can also notice that this is all observed with the precision of under 1 micrometer. So this is a very useful measurement to improve and to study and improve the systematic effects that go into the luminosity related to the beam dynamics, and it is already used to benchmark the beam effect simulations in the VDM regime. Okay, so let me conclude now. As I tried to show, the BCM1F has been now fully commissioned and operating very nicely, proving to be reliable and robust. And it has continuously provided CMS and LHC with the background measurements and luminosity measurements, and also based on the regular emittance scans, we are able to give feedback with the independent and non-destructive transverse profile measurements, as well as the per bunch orbit displacement. So there is still a long way ahead BCM1F that needs to be done for the precision luminosity measurement. And first of all, there is still a lot of work ongoing on the per channel BCM1 performance. And then we await the dedicated VDM calibration session, which is necessary to give a good measurement on the sample that we currently have. And of course, to do that, the many other systematic effects has to be considered. Thank you very much for your attention on behalf of the BCM1F team.
Thank you for your clear presentation on an impressive system. Any questions from the audience? Maybe I can start off. You mentioned a red heart ASIC that you probably have in the tunnel. So does this ASIC age over time, and do you have to recalibrate if that happens?
So this is this ASIC was basically designed for the Run 2, and it was actually designed here in Krakow at the AGH University. Just a side note, but it was operational during Run 2, and there was no proof of the aging during that time.
Okay.
So hopefully
it stays that way.
Yeah.
Okay, thank you. Any other questions? If not, let's thank the speaker again.
Thank you.
Okay, our next speaker is Jonathan Jarvis, and he is a scientist also at IOTA at Fermilab, and he focuses on a variety of R&D topics in accelerator science and technology. He currently leads Fermilab's research program in optical stochastic cooling, and that's what he will be talking about.
Okay, thank you very much. It's a talk about feedback, and I propose a collective exercise in feedback. If I move away from the microphone, somebody do this, and I will adjust based on the amplitude of your, okay. So I come from IOTA. We are an R&D facility at the lab. since it's been a few years since everybody's been together. And by the way, this is my first IBIC. I found it a very interesting and warm community, so I think we'll be back. And I want to include an introduction and an invitation. Yes, all right, thank you. See, it's working. All right. So we're a dedicated R&D facility. We have 3 machines. The first is an SRF LINAC 300 MeV Tesla type ILC style cryomodule with a couple of capture cavities. Then we have a proton injector that we're standing up, 2.5 MeV protons. And then the centerpiece of the facility is the IOTA ring. So if the things you see here today are interesting, we have lots of ways to test lots of different techniques and diagnostics. So please reach out. We're always interested in growing the collaboration and the portfolio of things we work on. That portfolio is dominated by the IOTA physics. And you can see the main topics here. The one we'll talk about today is the advanced beam cooling part of our portfolio. Dominated by optical stochastic cooling. But the main thrust of the program, you heard Sasha talk a little bit about, in fact, having Arnold and Sasha as precursors to this makes it a lot easier, because we'll talk about interaction of radiation inside undulators. We'll talk about the single electron capabilities of IOTA and what we did with this OSC program. So that's very helpful. But there's a mandate that we always produce an interesting video in every experiment. So here you see the beam operating on integer resonance, which is an interesting thing to do to a beam. And then you also see the single electron sort of operation. Okay, so stochastic cooling, without question, is what enabled the era of the proton-antiproton collider. Led to the discovery of the W and the Z bosons and the top quark. Here's a simplified OSC, stochastic cooling system. Basically, it's just a feedback system where we have a pickup that's going to sense the phase space of the beam in some granularity. It's in the microwave regime, so a few gigahertz bandwidth typically. We have a kicker that is very similar in structure, and then we have some sort of signal conditioning chain between those two. So we pass through the pickup, we sense the beam, we amplify that signal, and then we apply it back on the beam at some appropriate betatron phase advance later in this diagram. This sort of system, it requires you do a little trick, which is to randomize the phase space between the kicker and the pickup and subsequent passes through the system. Okay, so if you do this, two terms arise. There's a cooling term that's linear in the gain, and then there's this heating term. And so you want to operate at this sort of optimal gain condition where you're balancing those two effects. But the takeaway here is that you need to sense the structure of the beam, and you need to take the correction and apply it back in a way that reflects that structure that you measured. So that also means you can't randomize the ensemble between the pickup and the kicker. And I must make this system as wideband as possible. And if I can do this, then I slice the phase space more finely, and then I can move to a higher gain condition and get faster cooling, fewer passes through the system. Okay, so the way you do better, one way you can do better, is to go to this optical stochastic cooling. And so in this case, instead of slicing the beam with centimeter scale microwaves, we're going to do it with 50 femtosecond optical pulses. Okay, so it's a very, very granular sampling of the phase space. It proceeds as follows. You can recognize the same sort of elements. We have this pickup undulator that's going to generate a pulse for each electron. And we have n periods in that, so it's n times the wavelength. That's how long the pulse becomes. Then we take that light pulse and the particle, and we separate them with a magnetic bypass. And so this bypass does two things. It gives you room for the optics, for the light, and then it also lets you encode the phase space deviation for each particle onto its arrival time at a downstream kicker undulator. Okay, so you saw this nice talk yesterday where we're interfering the radiation from two undulators and then extracting information about the phase space from that. This is similar, you got the two undulators, but you also have this added effect where you can have each particle talk to its own radiation. And so we have this sort of phase stabilized situation between that wave packet and then the particle's trajectory in this downstream kicker. Okay, so how does it work? If you look on the top right, you're sort of autocorrelating the trajectory of the particle in the kicker against its pickup radiation. And as you do this, you find some longitudinal alignment condition where you're getting lots of energy transfer. And the sign and the sign and the magnitude of that energy transfer depends on that momentum deviation that each particle has. And it's happening to every particle the same way, but independently of one another. Okay, so the neighboring particles that are in sort of the temporal response of the integrated system, that bandwidth, they're going to talk to each other through this sort of diffusive force that's basically the same thing that you saw in the stochastic cooling equation. Okay, so this is a 1D thing. We're changing the energy of each particle through this interaction. But by being clever with the optics, the coupling in the bypass, and the coupling in the rest of the ring, you can actually distribute this cooling decrement freely between all phase planes. Okay, so if you have a downstream detector, what do you see? You see something that looks like just interference of the radiation from two undulators. And if I tune that delay, I'll go through these phases where I get totally destructive interference or totally constructive interference. Again, this is controlled by this mapping where you see the simple linear form of it here, where we have a longitudinal component that's sort of the M56 or the R56 of this chicane that's mapping energy deviation onto longitudinal position change. And then you have transverse terms, and this is the coupling we mentioned that gets you into 2D cooling. So you can also couple the bypass and pump up those terms so that if you have dispersion in your undulators, then you can transfer the cooling into the horizontal plane. So this is the trick we play. And then if we operate on a difference resonance, we couple the transverse planes elsewhere in the ring, then we can get full 3D cooling. Okay, so now I've got a situation where I've barely changed the momentum deviation of a particle, and I've gotten this relatively large change in its emitted energy. Okay, and so if you look at how much we lose in one turn, it's only 13 eV from the whole ring at 100 MeV electron energy for the optics we use. But these undulators, they're only changing the energy by like 100 millieV. So it's a very, very small effect on top of the overall synchrad loss on each turn. But we've engineered this system, this interference, so that that slope is very high. Okay, and if you know about storage rings, the slope of that loss function, that's proportional to the damping rate that you observe for normal synchrotron radiation damping. So we've engineered an artificial system that increases that synchrotron radiation damping rate, and we can do it by about an order of magnitude. So it's quite strong. Okay, but nothing's free. So there's a finite wavelength, and this means that I can't just have an arbitrarily high momentum deviation that still experiences this same cooling force. In fact, there's a limited aperture in phase space. Now, of course, you can engineer this by turning all your different knobs on the system design, but it gives rise to cooling and heating zones in phase space. So this is what that looks like parameterized by betatron and synchrotron amplitude. And so I go out to a high enough amplitude, the direction of the cooling force inverts, it becomes a heating force. And if I detune the system by half a wavelength, as it is now, you see that the fundamental mode is a heating mode, so I can blow out the core of the beam. And so this is very interesting because there's this longitudinal dynamics going on, but I also have the ability to like structure the phase space force. And if I do this in like interesting time-varying ways, then there's a hope that you can use this for sort of generalized phase space control, which is quite exciting. Okay, and there's another trick you can play, which was not available to the original stochastic cooling. All of the particles were sort of in the same mode, transversely. But with this, the short wavelength of the light, the diffraction limited size of those coherent modes can be smaller than the beam. So I can blow up the beam in the undulators and subsample the phase space. It requires that I kind of match the light and the beam transformation matrices so that a particle doesn't emit light and then miss it in the kicker. But you can do this sort of thing to artificially increase or effectively increase the sampling bandwidth. So that's also very exciting. You can kind of give yourself an order of magnitude or more sampling density this way. Okay, so this is sort of what it looks like in IOTA. We have a stage program that has two components. The first we're doing at 1 micron. It has sort of simplified optics. It's basically the simplest thing you can do that is sort of guaranteed to work. And so that's where we started. And then the next thing we do is a more complicated amplified OSC program, which will probably be at 2 microns. We operate in the bottom experimental insertion in IOTA. It's a 6-meter straight, and we occupy the whole straight, as you'll see. So why, this is kind of simple in principle. So what are some of the challenges? Well, we have to overlap these coherent modes to kind of 100 microns and 100 microradians. We also have to have stability, temporal stability, at the order of like a few hundred attoseconds for this to work. Because if the beam is sampling many different phases of this force, it's going to average out to basically 0, and we won't see anything. And then there's just the practical considerations, building this functionality into this limited space that we have available. Okay, so at IOTA, we sort of reconfigure everything for one topic, and that's what we did here. So you see we have bare girder. This is like October of 2020. And then we go to sort of full girder with this very high density, complex apparatus. So this is talking about collaboration and things. This is the sort of thing we'll do for an interesting science target. Key components of the system, you have the precision bypass there with the 4 chicane dipoles. You also have the delay stage that we use to fine-tune the longitudinal alignment of the system. So we have 2 plates, we're changing how much glass the light goes through. And then this gives us sort of tens of nanometers control of that relative delay. And then we have a lens stage that's in vacuum, sort of hexapod-like manipulator that's letting us control our optics very precisely. Okay, so some of the diagnostics we'll need. We'll need to see all of the phase space, so we're at least projected down. So we need to see beam images from our synchrotron radiation stations, and we also need a streak camera that can look at the longitudinal distribution projected down. We also have to be careful about the alignment, so we have an alignment laser that is basically matched into that. It's kind of what the pickup will radiate, so it's matched into that same mode, and we propagate that through all of our optical lines and diagnostic lines so that we can kind of easily align everything and be sure that we know in a global sense the relative alignment of these 2 beams. So in the bottom right you see that we've got the radiation from the kicker and the pickup, and they're simultaneously on 2 cameras. We take these 2 cameras that we call undulator radiation BPMs. They're imaging from different source planes, one upstream, one downstream, in the kicker undulator. And then because we have those 2 planes and we have this alignment laser, we can kind of get a very good feel of the angular and spatial alignment of those 2 coherent modes. So you have to overlap that, and then you have to sweep through the temporal delay budget. Okay, so we use 2 main methods to look at the OSC. The first is just a very slow delay scan, where we build up this sort of autocorrelation that we saw earlier, where the beam is exchanging energy in different directions, different amounts. So we sweep through about 30 wavelengths, so that's the entire thing, kind of 16 periods plus 16 periods. We're doing that very, very slow. And then on the fast toggles, we're snapping to the optimum cooling configuration very quickly. It's not as quick as OSC, but it's fast enough that all the other system parameters are basically the same. We did it for 1D, 2D, and 3D successfully with about the same cooling in all cases. And we have to re-optimize when we do this. But once you're optimized, the system is actually very stable over the day. You may have to make small tens of nanometers adjustments in the delay, but it's very reliable, very stable. So this is what it looks like. So we're going through that sweep, and you can see the streak camera image on the bottom, the interfering undulator radiation on the top left, and the transverse distribution on the right. So you see we're going into heating modes, cooling modes, heating modes, cooling modes. And the beam is getting blown out and compressed. And right about here, they synchronize, and it's nice, tight cooling and heating. Right? Okay, so when you project all this down into the 3 planes, this is what you see. So these are RMS fits on the side. This is showing, the middle one's showing you the alignment of these cooling and heating zones in the maximum aligned condition. And when you calculate what the bandwidth of the system is, it's on the order of 20 terahertz. So this is what you expect. And that's about 2,000 times greater than sort of state-of-the-art stochastic cooling systems that you can make. Here's an example of fast toggles for all of the different configurations. So you just see in a matrix view, you know, the 1D, 2D, 3D, and then the 3 phase planes. And then here is one where we look at just the Y distribution, because when the lattice is coupled, the emittance is shared, and it's enough just to look at one of those planes. So we're looking at the Y distribution and the street camera when we toggle, and you can see the compressed distribution relative to the uncompressed distribution. It's about 9 or 10 times stronger than the normal synchrotron radiation damping. We back that out from the beam sizes and a little model of the IBS. So that's about 60% of what we expected from theory, from SRW simulations of the actual radiation and the interaction. So we're very happy with that. That's not bad. Okay, but the phase space structure, I mentioned that we have this interesting structure going on. And so this cool thing happens when you go in the heating mode. You can see in this normalized phase space, you see those black trajectories. That's sort of where particles would go. So they're accumulating at these 2 first order attractors for the heating mode. One is high synchrotron amplitude, one is high betatron amplitude. And then it's low in the other plane. So the high synchrotron is low in the betatron and vice versa. And you can see these 2 populations of particles distinctly. When those forces are about equal, they all get, it's kind of evenly distributed between these 2 attractors, and you can see the populations very distinctly. You can even see the little dispersive dog bone-like shape in this core on the transverse BPM. Okay, so the single electron stuff in the last couple of minutes here. So I'll skip how we do it and why we do it and all that. Sasha laid that out very nicely. But what we did was basically we take a SPAD and we're looking at a slice of that fundamental undulator radiation. And then we can, as we do these sweeps or these toggles, we can look at how many photons are arriving. And we're time stamping those photons, and then we can look at dynamics that we wouldn't be able to see otherwise with the full beam. So we engineered the system so that for a certain level of betatron excitations, when we hit a gas molecule, it will still be able to capture the photons, but sometimes there's some loss that you'll see. Okay, so does it work? Yes, it works. If it works for the beam, it's got to work for one particle because it's sort of based on the one particle. But this really hits you over the head with it. We're just looking at timing. We bin that up, and we see the same sort of structure. When we're in the cooling mode, we see rapid suppression of residual gas molecule excitations of the particle. When we're in the heating mode, you see the lobe structure where we're blown out to high amplitude. And then even sometimes you see where we'll be in the heating mode, but the particle gets hit by a gas molecule, and that moves it out of overlap with its radiation. There's a mismatch. You remember the transformation matrices not matching? They don't really match. So if we get excited to too high an amplitude, we miss the light, and that turns off OSC. So you'll see these regions where OSC effectively gets turned off in the heating mode. Okay, there's a closer view. And then here's a sweep. So everything's basically the same. The cool thing to note is the total event rate. This green curve, it's modulated with like 80%. So it's almost completely constructive and destructive as expected. And then Sasha already told you we can fit, this one we did with an FFT, so we just do an FFT of all the raw data. That gives us immediately amplitude and phase of what the particle is doing. For that extraction of amplitude and phase, we're using a high resolution PMT that's faster than our SPAD detectors. But so that gives us a synchrotron motion, as you can see in this graph. And what we expect is that as the particle goes through its synchrotron oscillation, it's sampling different phases of that loss surface. So you'll see more or less radiation emitted as it oscillates. So this is like the other side of the coin of tuning the delay and seeing those big emission oscillations. Here we're actually just letting the particle get excited randomly, undergo its oscillation, and see the change in emission probability. Okay, and so here's what it looks like. So if you just naively bin up all the photons, you see sort of exactly what you expect. Okay, so you see this sinusoidal modulation for small amplitudes. All right, we're in the cooling mode, so the amplitudes are necessarily small. The experimental data is in the center, and the theory is on the right side there. But what's cooler is the heating mode. So the heating mode, you're out at very high amplitudes, so you're going to sweep across an entire zone, and that ends up having a quite complicated structure for how many photons you happen to emit at a given synchrotron phase. You can ignore this little dark notch that's on the left side of the right plot. This is basically if you just kind of naively reconstruct the phase space and say where are the photons coming from, you can see exactly what's going on. It gets out to that maximum where that surface is peaked, and you see the most photons there, and then it moves past that in energy deviation, and it goes back down, and then it comes back up when it's coming back, and then it goes to the other side where you see these two minima symmetrically distributed. So it turns out that you can sort of back out things from this, like that we were kind of like 30 or 40 nanometers misaligned temporally. That's not something that was easy to do with the beam, but with the single electron, you can't miss it. So that's very cool. Okay, and then you can also see the same phase space dynamics, the structure for high amplitudes in the single particle case. But with the single particle, it can obviously only be in one attractor at a time. So you see these bistable transitions between those two attractors. And here you've got those two modes, and then I've got the transverse BPM image for those two cases. So in one you can see indeed it's a high synchrotron amplitude, low betatron, and in the other it's high betatron, low synchrotron. And then some movies of what it's doing in each of those modes. Okay, so conclusions. Hopefully I've convinced you it's sort of an interesting topic at this intersection of doing cool fundamental stuff, but also with an eye towards operational cooling systems eventually. It was very successful. If you want more details on the methods, it just appeared in Nature a few weeks ago, so you can look up that article. And lastly, a little bit of an advertisement. We need a postdoc. So if this was interesting to you, there's a job link here. We're going to go up to 30 or 40 decibels of power gain in the next version of this experiment. This gets us within throwing distance of the optimal gain condition. So this could be very exciting and interesting and relevant for future applications. Thank you to the entire team. Thank you very much for having us out, for inviting us, and we'll be happy to take some questions if there's time.
Okay, let's thank the speaker. And do we have a quick question? There we go.
A quick philosophical question.
Oh,
What's
good.
the emittance of a single electron?
Sound of a hand clapping, right? I mean, so over time, it will explore the entire phase space that the normal beam would. I mean, it's,
But when I think about
it's
a bunch of
damping and quantum
electrons,
excitation.
if I think of a bunch of electrons, I separate the phase space from the motion of the centroid. So you're kind of defining the emittance by how much its centroid is moving.
Yeah.
So
Okay. So
that's why I said it's a philosophical question.
It's zero then.
Yeah.
Yeah.
All right. Well, I think thank you again for a unique presentation. And then that's the end of the scientific program, and we'll go over to the organizational part of this session. And first up is Tonya Batten to talk about the next IBIC in Canada.
Okay. All right. Okay, good afternoon. My name is Tonya Batten, and I'm a member of the beam instrumentation team at the Canadian Light Source. So first off, I want to thank the organizing team for letting me talk to you today. I also want to congratulate and thank the organizing committees and support staff for the tremendous success of IBIC 2022. I also want to thank the attendees here today for engaging or for your submissions and for the engaging and informative contributions. I also want to take this opportunity to extend an invitation to the 12th Annual International Beam Instrumentation Conference, which will be hosted by the Canadian Light Source in Saskatoon, Saskatchewan in September of 2023. So for those of you that have not had the opportunity to visit us, we're located in Saskatoon, Saskatchewan, so we're in central Canada. We are located about 350 kilometers north of the US border, so above North Dakota and Montana. The Canadian Light Source is located on the beautiful University of Saskatchewan campus, which is one of Canada's top universities in the vibrant city of Saskatoon. Saskatoon is located on Treaty 6 territory, which is the traditional homeland of the Métis. The University of Saskatchewan is proud to claim 2 Nobel laureates, Gerhard Herzberg and Henry Taube. So Dr. Herzberg is a world-renowned scientist whose experiments fundamentally changed the understanding of how molecules emit and absorb light. Dr. Taube is a Canadian-born chemist who won a Nobel Prize in chemistry for his work on the mechanisms of electron transfer interactions. Saskatchewan is also the birthplace of Sylvia Fedoruk. So Sylvia Fedoruk is a professor of oncology and an associate member in physics at the University of Saskatchewan. She was instrumental in the development of the world's first cobalt-60 unit, so the cobalt bomb as it's more commonly known. And it was the first of its kind to successfully use targeted radiation to treat cancer. So a little bit about Saskatoon. We're a city of approximately 300,000 people. We're located on the South Saskatchewan River. We're a budget-friendly city known as the City of Bridges, and we exude welcoming vibes. Our city slogan is Saskatoon Shines, and that's definitely true. We're one of the sunniest places in Canada, and we actually experience about 2,200 hours of sunlight per year. Now, some of you might be worried about our extreme weather, and I want to assure you that Saskatoon and Saskatchewan in September is an absolutely beautiful place. Warm, sunny days give way to crisp, cool nights as the province erupts into glorious displays of color. So Saskatoon is also a fast-growing technological hub. So in addition to the Canadian Light Source, the University of Saskatchewan is home to th2 and the Saskatchewan Centre for Cyclotron Science. So th2 stands for Vaccine and Infectious Disease Organization. This organization has a history of rapidly developing solutions for emerging human and animal infectious diseases. So th2 has been a leader in the Canadian response to COVID-19. The Saskatchewan Centre for Cyclotron Science is a state-of-the-art facility which supports innovation and nuclear imaging and therapy in live specimens. The Canadian Light Source is also home to the Medical Isotope Project. So the MIP, as we call it internally, uses a small, high-power industrial electron linear accelerator to produce a flux of high-energy X-rays. These X-rays strike a target and produce molybdenum-99, which is then used in diagnostic and therapeutic medicine. Now, the Canadian Light Source is a third-generation light source which began user operations in 2005. Since then, the Canadian Light Source has enabled 4,000 scientists from 41 countries to publish over 6,000 scientific papers, which highlight discoveries in a wide range of fields. The Canadian Light Source has contributed to over 850 international scientific collaborations. Now, the Canadian Light Source, or the CLS, is the only synchrotron in Canada, so it is one of the largest science projects in Canada's history, with more than 100 academic, government, and industry scientists from around the world using the CLS every year. Our scientific programs focus on health, agriculture, energy and the environment, and advanced materials. So we're very excited to invite you to both our facility and to our city. So I want to talk to you a little bit about the program that we're organizing for IBIC 2023, which will include an extensive scientific engagement and incorporate a number of excursions that allow you to experience Saskatchewan's diverse heritage. So the main conference venue will be TCU Place. TCU Place is located in beautiful downtown Saskatoon, just minutes from the Saskatchewan River. It's a creative and inspirational environment featuring over 100,000 square feet of space for presentations, poster sessions, exhibitors, meetings, and extensive social engagement. Both our accommodations and our hospitality are outstanding. Whether you're interested in modern amenities or timeless historical experiences, we have options for you. There are wonderful things to explore in the city of Saskatoon. The Meewasin River Valley has nearly 80 kilometers of walking trail that runs along both sides of the South Saskatchewan River. Reader's Digest listed the Meewasin Trail as one of the top 10 greatest hikes in Canada in the fall. In addition to our wide open spaces and welcoming hospitality, Saskatoon also has a vibrant art and culture scene. So we intend to host our welcome reception at the Remy Modern Art Gallery. This art gallery has received international acclaim, and it provides a Canadian perspective on global, modern, and contemporary art movements through a mix of regional, national, and international programs. The conference dinner will be held by Champetre County, and will have a Wild West theme. So Champetre County is located 35 kilometers outside of Saskatoon. It's a special event venue that offers catering and themed activities, which will leave you with an inner peace, having experienced the simpler things in life, while learning about Saskatchewan and the prairies in a unique way. So on the Saskatchewan license plates, you'll see the slogan, "Land of Living Skies." And the inspiration behind this slogan comes from the awe-inspiring sunrises and sunsets that we experience, and the spectacular northern lights. There really is something for everyone. We've seen an amazing evolution in the craft beer and spirits industry, with a focus on locally grown ingredients like the Saskatoon berry, which is native to the region. If you're interested in sports, we also have the Saskatoon Blades, which is a junior hockey team that plays in the Canadian Western Hockey League. Now, not many people know that we actually have two national sports. Hockey is our national winter sport, and lacrosse is our national summer sport. So as such, we also have a professional lacrosse team in Saskatoon called the Saskatchewan Rush. Saskatoon is also home to Wanuskewin Heritage Park, which is home to Canada's longest run archaeological dig site. So this site celebrates our First Nations culture and dates back over 6,000 years. Saskatoon is also home to the Western Development Museum, the largest human history museum in Saskatchewan, with a collection of almost 80,000 artifacts, with a focus on 1910 boomtown and innovation in Saskatoon. We look forward to welcoming you to both Saskatoon and the Canadian Light Source in 2023. Thank you.
That's it. So, do I need to bring a coat?
So in September, we tend to have larger variations in temperature. So we tend to be 5, 10, 15 degrees in the morning, 20, 25, 30 degrees in the afternoon. So I would definitely dress in layers.
Okay,
Yeah.
thanks. Oh, and the next stop is the closeout, and there's Adriana.
Okay, so here we are. almost at the end of the conference. Yeah. And what about, okay. So I have a few closing remarks. First of all, I would like to thank you all for the participation. We have been here for almost 4 days in Krakow. So regarding the registration statistic, we had 246 participants registered, where 141 was the regular participants. Then we had 37 students registered, 33 companies attendees, and also the 35 people of the local organizing committee, and also including the JACO team. So as you see here, we have a distribution along the world. So the 84% participants from Europe, and we have 9% from America and 7% from Asia. And I think that it is even less because there were also some Chinese people registered, but in the end they didn't arrive. And regarding the distribution along the countries, so you see that the most participants are from Germany. We also had granted students this year, so it was thanks to the surplus from IBIC 2019, we could grant 12 students. In the end, one of the students didn't arrive due to the visa problem. But those students were here, and they were helping also at the organization of the conference, and thank you for that. Also, regarding the JACO team, we had the editor-in-chief, which was our colleague Grzegorz Kowalski, and also Volker Shah, who was supporting him and was doing a lot of job before the conference as well. So we had 157 or 8 abstracts registered in the SPMS, and from Volker today, this is the update that we had like 125 papers submitted, and 117 is already prepressed. We also had 21 companies serving as vendors and sponsors of this conference, and also one partner of this conference. We also had a honorary patronage of the Media Krakow, and also of Jacek Majchrowski, mayor of the city of Krakow. So I would like to also thank all those partners and sponsors to support this conference and to participate in it. Regarding the scientific program, we had 17 invited talks, included 2 remote talks. Those people couldn't come due to the travel restriction, one from China and one from Fermilab, also due to the visa problem. We have heard 2 outstanding, I would say, tutorials about the collimation and machine protection, and also on the beam stability, which is very, I think, hot topic now, especially for the small emittance storage rings. And we had 21 contributed talks. So also we had 3 poster sessions, and I think that it was very well organized, and there was really live discussion during those sessions, what you can see on those pictures. So I would like to, first of all, and we have also the Faraday Cup Award, which we handed to Dr. Ichar Lobach. Regarding the statistic, we had 9 classification topic, and you can see the distribution of the invited, contributed, and poster along those topics. So the less maybe popular were overview and commissioning and data acquisition, but this distribution is something similar to the other IBIC that we had in past. Also, when you see the distribution along the different countries, you can see that there is like 80% of Europe, which is, of course, understand since we have so many participants from Europe, and also there is 13% from the North America, also from Asia, like 8 we had, and from Middle East 1% about. Also distribution along the countries, so you can see also that here the winner is the Germany, and also we had quite a huge amount from the United States. And I would like to thank all the speakers and also the presenters for very great preparation of their presentation, and also all the chairmen for chairing those sessions within and keeping the time. So we had also the social events starting from the welcome reception. So we also could see the performance of Słowianki ensemble, and we were seeing that people really looking for contact due to this 2 years of break. I think this was the very good organized also during the session, that people were networking and discussing a lot during the also coffee breaks and lunches. And we had yesterday the dinner, and I hope that everybody enjoyed. At least I get very good feedback from this. And today we also will have a tour to Solaris. So the buses will come at 3 different hours, and you assign to this. So please check to which bus you are assigned. And also, I would like to mention that we had a little bit hard conditions to work sometimes due to those slides, but actually they were needed because we also were recording these sessions, and this will be available after the conference, and link will be available at the website. Also, the photos will be available at the website, so if somebody doesn't want to show his image or disagree to that, so please write us an email. Okay, so at this conference we also have selected the next European IBIC organizer. So this will be in Liverpool in 2025. With this, I would like to once again thank you all for the participation. Thank you to the scientific program committee members. Thank you also once again to the local organizing committee for a very good organization of this conference. And thank you all. That's all. With this, I'm closing the IBIC 2022 and see you next year in Saskatoon, I hope.
Right. Thank you. It was excellent, enjoyable.